participate, and then let me share my PhD in Geoenvironmental Science and MSc in Remote Sensing and GIS. In brief, my research focuses on monitoring and assessment of terrestrial environments, including forest, agriculture, urban, and disaster thematic areas, and capacity development. In the last 20 plus years of my career, I am empowering people to use emerging Earth observations and geospatial technology for making evidence-based decision to protect the pulse of the planet. So I want to ask you one question. Why do you think we need remote sensing for our region? Can anyone say anything? Why do you think we need remote sensing for our region? Yes, please.
Can you hear me, please?
Yes, yes.
Yeah, good morning, everyone, and Assalamu alaikum. For your question, I think remote sensing is a technique where you gain the information about something, about an object, with that object. Am I audible?
Yes, yes, yes.
Did you hear my answer?
Yeah, yeah.
Okay, thank you.
Great, great. Thank you very much. So I wanted to highlight that the why remote sensing needed, especially for our region. So Hindu Kush Himalayan region covers the highest mountain range in the world, where difficult terrain and high degree of inaccessibility presents a formidable challenge to collect, manage data and information. Earth observation data, in combination with emerging geospatial information technology, help us to access remote region and provide viable solution to bridge the data and knowledge gaps in this region. So in this slide, I want to highlight that the satellite imagery has the unique ability to provide synoptic views of large areas at a given time, which are not possible using conventional survey method. Dating back to the 1960s, Earth observation system has been providing consistent historical time series data. In line with the development of Earth observation system, GIT is emerging to make useful decision and analysis from the vast amount of data provided by Earth observation systems, as shown in this figure. The figure in the right shows a typical remote sensing system, where you can observe a satellite is acquiring the data from Earth, transmitting the data into ground station, a complete processing system to application products. The figure in the left is just a snapshot of the severe priority areas of Earth observation application for connecting space to village. So remote sensing is the science for collecting and interpreting information on target, which can be any objects or areas in the ground without being in physical contact with them. It employs electromagnetic energy. The keyword is electromagnetic energy in the form of radio waves, light, and heat as a means of detecting and measuring target. Remote sensing gathers information about the Earth from a distance, usually from aircraft or satellites, as shown in the figure in the left. It offers the ability to observe and collect data of any place of the Earth's surface relatively quickly, which helps to study, map, and monitor environmental consequences at local, regional, or global scale. It is cost-effective and gives better spatial coverage as compared to ground sampling. Therefore, it's an important source of data of GIS. Remote sensing data can be collected using different types of sensor mounted in various type of platform. We can look at the platform by grouping them into three major classes, that is ground-based, aerial-based, and satellite-based platform, as shown in this slide. Ground-based platforms are fixed at the ground for continuous monitoring of certain environment in the particular location. UAV drones, which is becoming very popular recently, and aeroplane are considered as aerial-based platform. These platforms are often used for quick survey and primary information acquisition, such as after the disaster event. For frequent and systematic large area environmental monitoring, satellite-based platforms are used. In this lecture, we will be more focusing on application of satellite-based remote sensing. There are 5 key components of remote sensing, that is energy source, platform, sensor, processing, and institutionalization. Sun energy used in passive remote sensing, also called optical remote sensing, and artificially energy generated energy from its own source, own systems used in active remote sensing, also called radar remote sensing. So you need to remember that optical remote sensing and radar remote sensing, we will be using these two words interchangeably. Platforms are covered in previous slides. Sensor is a device that receives electromagnetic radiation and converts it into a signal that can be recorded and displayed as either numerical data or an image. Data processing and institutionalization are also considered as key component of the remote sensing, which help visualization and analysis and make sure the utilization of the result and application. So this is a remote sensing workflow. Remote sensing process involves an interaction between incident radiation and the target of interest. The first requirement for remote sensing is to have an energy source which illuminates or provides electromagnetic energy to the target of interest. You can see in A. Remote sensing type is often categorized based on the energy source used in the data acquisition, that is passive and active. Passive type of remote sensing, we also call optical remote sensing, uses the energy naturally reflected, such as sun, or radiated from the object. Active type of remote sensing, we also call radar remote sensing, provides its own source of electromagnetic radiation to illuminate the object. As the energy travels from its source to the target, it will come in contact with and interact with the atmosphere it passes through. So this interaction may be placed a second time as the energy travels from the target to the sensor. You can see the later indicated by B. Once the energy makes its way to the target through the atmosphere, it interacts with the target depending on the properties of both the target and the radiation, as indicated by C as a target in the ground. After the energy has been scattered by or emitted from the target, a remote sensor collects and records the electromagnetic radiation, as you can see the satellite image in D. The energy recorded by the sensor has to be transmitted, often in electronic form, to a receiving and processing station in the ground, where data processing are processed into a digital image. You can see in E how it transmits the data into ground. The processed image is interpreted and visually and digitally to extract information about the target. That is, you can see the representation as GF. And the characteristics of an object can be determined using reflected or emitted electromagnetic radiation from the object. Each object has a unique and different characteristics of reflection or emission if the type of object or the environmental condition is different. Finally, applying the information extracted from the imagery about the target in order to better understand, reveal new information, or assist in solving a particular problem in decision making of institutions, which is I have shown here in denoting by G. So this is a remote sensing workflow. So it's very complete workflow. You can see from A to G. So it completes the whole from data acquisition to data interpretations. So let me turn off my mobile. I am receiving a lot of message there. I will turn off it so that there will be no disturbances.
Excuse me, sir.
Okay, so let's move to basics of remote sensing systems. I wanted to just highlight the passive and active remote sensing here. So this is an example of passive and active remote sensing. There are a list of satellites in both systems, such as Sentinel-1, ALOS Pulsar, or ALOS Avenue 2, Landsat series, and Spot Modis, Iconos, Quickborg. There are many other satellites for passive remote sensing. And then for radar remote sensing, the list is also similar, like Sentinel-1, ALOS Pulsar, ALOS-2, RadarSat, and others. So these also in the figure, you can see that the schematic diagram that can show that which one is a passive remote sensing. You can see these which is in the top of in the image, and then the active remote sensors sensing systems in the bottom. So here you can see an example. So this is an example data from ALOS-1 satellite representing the imagery, optical in the left and the radar in the right, taken by same satellite at the same time and location, but the sensors are different. So you may compare the data and imagine the benefits of the sensor. So one is you can see contaminated by cloud, another is cloud free. So another is the image in the right, which is cloud free. It's coming from the radar sensor. So you can have some kind of idea why those both sensors are very important to understand. So there is a long list. Let's walk through a little bit on optical versus radar. So we have to be very clear that the which sensor is a better suit for our needs. So if you understand, this is a very basic understanding, but if you want to do more details, then there are a lot of literature there you can search later. So optical remote sensing makes use of visible, near infrared and short wave infrared sensors to form images of the Earth's surface by detecting the solar radiation reflected from targets and on the ground. So here the keyword is a visible, near infrared and short wave infrared. So that is keywords you need to remember in optical remote sensing. And different materials reflect and absorb differently at different wavelengths. Thus, and then also you need to remember the wavelength as a keyword. We will be talking later. And thus, the target can be differentiated by their spectral reflectance signature in the remotely sensed images. Optical systems are nadir looking. You need to remember nadir looking. What is nadir looking? We will be talking later. Nadir looking is a keyword. So here also you can see that the panchromatic imaging system, there are three systems: panchromatic imaging system, multispectral imaging system, and hyperspectral imaging system. So you may read the slide later. Let me move ahead. And then this slide shows the about radar. Radar is a radio detection and ranging, refers to a technique as well as an instrument. The radar instrument emits electromagnetic pulse in the radio and microwave regime and detects the reflections of these pulses from objects in its line of sight. The radar technique uses the two-way travel time of the pulses to determine the range to the detected objects and its backscatter intensity to infer physical quantities such as size or surface of the roughness. There may be one mountain or there may be one building. So it will determine based on the time and then the backscatter intensity. Analyzing that, we can estimate whether it is a building, whether it's a mountain, and how the surface is there. Unlike optical, radar system consists of all-weather and all-day capabilities, allowing regular mapping of areas affected by heavy cloud cover, persistent rain, or extended darkness. Because radar has its own energy that sending to the object in the earth. It is not utilizing the sun energy, which which is utilized in optical systems. Um, the optical system cannot acquire data in such situations, such as if the area is heavily covered by cloud, or there is a persistent rain, as the rainfall is occurring there, and especially for instance, during this season, there are a lot of flooding and something, and during the flood, there may be persistent rain occur, and then also a lot of cloud cover can be observed. So, and then also you need to remember radar systems are side looking. So do you remember the optical systems are neither looking. So neither looking is optical system. Side looking is a radar system. These are the keywords, side looking and neither looking. We will be talking later in another slide. The signals interact differently with the surface than most other systems, providing interesting new information about the observed environment. So that is on radar. And here the electromagnetic radiation, the keyword was electromagnetic that I was highlighting in previous slide. So we need to understand this one. Energy from any source comes in the form of electromagnetic radiation. Look at the figure in the left. Electromagnetic radiation consists of electrical field, which is denoted by E, and magnetic field denoted by EM, and travel at the speed of light denoted by C. You can see very easily. It's very simple figure. The another figure shows an example of wavelength and the frequency. Wavelength is you can see which is denoted by lambda there. And this the wavelength represented by lambda is the length of one wave cycle, which can be measured as the distance in meter, centimeter, and nanometer between successive wave crests. Frequency refers to the number of cycles of a wave passing a fixed point per unit of time. Frequency is normally measured in Hz, Hz, equivalent to 1 cycle per second, and various multiple of Hz. So these two are inversely related to each other. The shorter the wavelength and higher the frequency, and vice versa. I know some of you are from social science background. Maybe it's difficult to see, but you don't need to understand all the physical things here. But what you need to understand that if there is an image, how to interpret, how to understand that image, and how you can use that image in your social science study. And we also have there some colleagues, some participants here from electrical engineering and computer engineering, and maybe the colleagues from electrical engineering, they understand the physical property of these things. And also who study physics in their undergraduates, maybe they also understand all those things. So as I said that you need to remember electromagnetic spectrum. So I wanted to highlight that keywords here in simple way. Here you can see the electromagnetic spectrum from very short gamma rays to very long radio waves. In Earth observing remote sensing application, we used passive electromagnetic spectrum from visible to infrared. As I said that you need to remember like visible, infrared, shorter infrared, something like that. So this is coming here. And active electromagnetic spectrum at microwave region. And microwave is something maybe different that you are using at your kitchen right now. And the microwave region here we will be using from the satellite may be different from that. And the visible spectrum is enlarged for easy understanding, which is in optical remote sensing often called blue, green, and red. We can see three colors, blue, green, and red. You may also note the corresponding spectrum presented in nanometer for each band here. Like you can see in the blue band is from 400 to 500, and green is 500 to 600, and then red is 600 to 700 nanometer of the wavelength. And this is an example. Look at the figure in the right. There are also sample figure you can see like the ocean, like water body, and another figure like in the photo here in the left you can see vegetation, and then also the bare soil here, so that you can just have an idea, you can imagine how it looks like in the satellite image, which is showing in the bottom of this figure in the right. So just a kind of interpretation here, high surface energy reflectance from water can be observed in blue region of visible range, where it is just opposite in the near infrared region. You can see the curve here, some lines here in the figure. Longer wavelength in visible and near infrared radiation is absorbed more by water than shorter visible wavelength. Thus, water typically looks blue or blue-green due to stronger reflectance at this shorter wavelength, and darker if viewed at red or near infrared wavelengths. If there is suspended sediment present in the upper layer of the water body, then this will allow better reflectivity and a brighter appearance of the water in the satellite imagery. The broadleaf and needleleaf coniferous vegetation samples have um, almost the same spectral response in the visible region. That is why they both appear green and would be difficult to discriminate, but they have a significant different reflectance characteristics in the near infrared, so that you can discriminate, and could be distinguished using data from this near infrared band. So vegetation species typically show greater differences in their near infrared reflectance characteristics than in the visible portion of the spectrum. So reflectance from soil is higher in mid-infrared as compared to other wavelengths, which is you can easily you can see, you can observe in this graph, which is also shown in this like dotted line for soil, and then green line for vegetation, and then the blue line for reflectance from water, and then corresponding sample image that is taken from satellite you can see in the bottom, and then the how it looks like in reality in the ground you can observe in the left side. That is a photograph taken. So you need to understand what types of remote sensing images will be there to analyze. So presently there are several remote sensing satellites in operation. Some are sun synchronous, called a polar orbit, where the satellite always crosses the equator at the same local solar time. Most of the Earth resource satellite, Landsat, you may be going to use, Spot, Elos, Iconos, Quickbird, etc. are sun synchronous. Generally, these satellites are orbiting at lower than 1,000 kilometers away from this Earth. So, for example, maybe Landsat is maybe about 700 kilometers away from here. Something, and Sport maybe something similar. Elos is also something similar, maybe 800 kilometers away. You can search in Google how far they are from the Earth. And some satellites are in geostationary orbits, where satellites are located directly over equator at very high altitude, maybe more than 30,000 kilometers or 40,000 kilometers away from this Earth, and it revolves in the same direction that the Earth rotates, west to east, so that the same portion of the Earth's surface can be observed at all time. So these satellites are especially used in meteorological, communication, and broadcasting applications. For example, the satellite names are like GEOS, GEOS, Metrosat, EduSat, Galaxy, or there are maybe some other communication satellites. So note that different satellite systems have different characteristics. That is, for example, spatial resolutions, number of bands, and have their own importance for different applications that we are going to discuss in next slide. So here each satellite has specific science and application missions. So you cannot expect everything from one satellite. So there may be for different applications, and there may be different applications. Here I am showing that some satellites and their applications, that are the representations. You may observe satellite names diagonally upward from left to right, and their major missions applications such as crop monitoring, topography mapping, soil moisture mapping, etc. And here, so since I already alert you that you need to remember nadir, and I also alert you that you need to remember like a side looking or nadir looking view. So this is a nadir looking view. Nadir, it refers to the images taken by a space-based sensor camera pointing to the vertical direction below in the earth ground. Pointing to the nadir means that the camera axis in the direction of the lens is perpendicular to the ground. So here you can see the nadir picture also. Uh, while images are taken with the camera axis not perpendicular to the ground, are called oblique image. So most times, like you and you can take the pictures of yourself or other colleague or the landscape, like using your camera or your smartphone. That maybe most times it's oblique view. So you may see different schematic example of the field of view here. In other view, you may expect image data from straight down, while in low oblique view, you can expect image tilted but not horizon visible, and in high oblique view, you may expect imagery data tilted with horizon visible. In this slide here, I wanted to show you that how remote sensing imagery looks like in nadir view, low oblique view, and high oblique view. And they have different applications there, so that there are still people or sensor or platform they're taking, the remote sensing system is taking those kind of data set. So let's see what are the characteristics of remotely sensed imagery. You need to understand the major characteristics. So I wanted to highlight that the remote sensing systems differs in the level of details or resolutions they can capture. Data are available at a variety of resolutions. We will cover 4 types of satellite resolutions here. That the one is a spectral resolution, another is a radiometric resolution, another is a spatial resolutions, and temporal resolutions. These all are very important. You need to understand that. So, and most often you will be using spatial resolution and temporal resolutions. But if you understand those characteristics, then you will not be very confused. So, spectral resolutions refers to the degree to which a satellite sensor can distinguish or resolve features of the electromagnetic spectrum. We will be seeing how spectral resolutions we can imagine in next slide. And similar, I will be explaining radiometric resolutions, spatial resolutions, and temporal resolutions. So this slide shows highlights the spectral resolutions here. The specific segment of the electromagnetic spectrum that are recorded by a system refers to its spectral resolution. Some systems contains bands that cover broad range of electromagnetic spectrum, while some system contains a band that covers very narrow segment of electromagnetic spectrum. You can see, for example, here in the below, if you look at this, if you are able to observe the pointer of my mouse here, you can see the bands are here are very small, but sometimes you can see very long bands here, like here you can see, and then also you can see here, and these are the satellite name here, like Sentinel-2 MSI, Landsat 8 here, Landsat 7 here, and this is Aster, and this is MODIS. There are some representative satellite I am showing here. There are many other satellites. And then so recording very narrow segments of the electromagnetic spectrum allow for greater detail. For example, here you can see in the MODIS in defining spectral signature. High spectral resolution is achieved by narrow bands which collectively are likely to provide a more accurate spectral signature for discrete objectives than broad bandwidth. For instance, you can see here Landsat 7 provides data in 8 spectral bands. There are 8 spectral bands in the Landsat, like band 1, band 2, band 3, band 4 here, 5, 7, 6, right? And then here also 8. No? And then this is while Landsat 8 provides 11 spectral bands. This is a Landsat, you can see 11 band here in different wavelength. You can see the wavelength here. And then similarly, you can observe Sentinel-2 data with 12 bands, Aster satellite data with 14 bands, and MODIS satellite data with 36 bands. So different spectral resolutions will have different Earth system monitoring applications. That's why they are in the different satellite provides different bands there. And come to the radiometric resolutions. You can look at all those pictures, and then I think you can visualize how different radiometric resolution will provide how detailed in the imagery. So the radiometric resolutions of image data in remote sensing stands for the ability of the sensor to distinguish different gray level or grayscale values. It is measured in bit. A bit is a binary number that is in 0 or 1. The more bit an image has, the more grayscale values can be stored, and thus more differences in the reflection on the land surface can be spotted. If you look at here, like 1 bit quantization, 1 bit will have 2 levels, 0 and 1. You can see just black and white. And then if you move further, like 2 bit, 3 bit, 4 bit, 6 bit, and 8 bit, you can realize that how much detail you can expect when the bit increases. There is also 16 bit. I have not put that image here, but just this image will provide you a kind of knowledge that the differences between, and so it will help you to understand radiometric resolutions. Let's move to spatial resolutions. Look at very carefully these images, and the schematic diagram in the left, and then the real imagery, and that is from satellite in the right. So the spatial resolutions in terms of geometric properties of the imaging systems is usually described as the instantaneous field of view, IFOV. The IFOV is defined as the angle which corresponds to the sampling units on the ground. You can see that the like 1 meter, you have a many sampling units here, and then if you see in the 5 meter, you have a very less sampling unit, and then if you see in 30 meter, you can see the sampling unit is just 1. So these kind of things you need to understand. So ground resolution is the minimum detectable area or distance on the ground, and in some cases the projected area on the ground corresponding to the pixel. So that we can call the pixel here, and we also call ground resolution. Depending on the study objective, you can select different spatial resolution, but understanding of spatial resolution impact in analysis is important. Here is important. So if you see the houses here, in the figure, then a house can be represented in the image with different spatial resolutions. You see here. You can also compare the spatial resolution as shown in the satellite imagery here. The figure, the satellite imagery in the above is a Landsat imagery, and then the below is a old view 2, which is like a 0.5 meter spatial resolution. So how much detail you need, what is your purpose, the purpose will define it. So if you wanted to make a land cover map of Pakistan, then maybe in the very high detail of like old view 2 imagery, it's not useful. Maybe Landsat image is useful. If you wanted to see make the map of your residential area that you are staying right now, then maybe you need a kind of very high resolution imagery, something like old view 2 imagery, because you wanted to map every detail near to your house. So so here the table shows an example of current satellites which are available in the space, and their corresponding spatial resolution from 0.41 meter to 1000 meter spatial resolutions. So you may wish to experience how Faisal Masjid. I think most of you have been there. Faisal Masjid? Or maybe some of you
Yes,
are from Islamabad, no? You are
yes,
familiar
sir.
with that.
Yes, yes.
Yeah. So I have been there in 2018 December. So I took a picture, the below that you can see that the picture, the table below, and then the right side is the satellite imagery. That image is available from Google Earth. You can visit Google Earth and you can see that image. And it was acquired in 18 June 2019. That means that image is taken after I visited there, and it looks very beautiful. You can see the how the Faisal Masjid can be seen from space. You can see even you can count individual tree there in their garden, and then this masjid, the surrounding, how it looks like. So it's a really useful view, so that you can map it. You can digitize all these lines if you wanted to see the road there, and then you can digitize these how much of land is occupied by this masjid, something like that. So let's go to temporal resolutions. And temporal resolution is it's related to the repetitive coverage of the ground coverage by the remote sensing systems. So for many of the physical and cultural features on the landscape, there are optimal time periods during which these features may best be observed. I'm talking about seasonal. So these optimal periods might be seasonal or could last only for a few days of a week. So in the case of some application, the time interval at which remotely sensed data are acquired becomes an important factor. If you are, if your objective is to monitor rice plantation, then you can imagine how fast rice grows. So there may be sowing season, there may be the growing season, there may be harvest season. No? There are already three kind of seasons will be there if you are looking at in that much of detail. So for example, to monitor crop growth, images should be obtained at a predetermined time interval within a year period. However, to monitor urban growth patterns, maybe you are not interested to monitor within few months, no? Maybe yearly. So image acquired at different intervals of a year or more may be appropriate for urban monitoring. You can see here kind of urban activities here acquired by the satellite images. Like in 2000, you can see how the land looks like. In 2007, in 7 years of time interval, you can see there are a lot of buildings came in. So there is a settlement bubbles in Manohara, that's from Kathmandu. So you can see the detail in city profile in Thapa et al. So here it's a look at this figure. This is more high temporal resolutions. I'm showing here kind of forest change in Farah, and this is a forest change monitoring applications using JERS and LS pulsar data. And you may see grayscale image taken in different time stamp. You can just note that. And then corresponding forest, non-forest map that is showing in the green and then the yellow color, and then also you can see the river that is in the blue. And then also another column you can see the in the map is the forest change map. So look at the figure very carefully, very carefully. Just look at figure from 1993 to 2010. I hope you have looked at it. Can anyone articulate? Can anyone say what did you see in 2007?
There is a lot of deforestation in 2007, and also there is a lot of area that is not forest anymore. So there has been deforestation as well as maybe bare area because there is no forest over there. So it's a non-forest area. The yellow one is non-forest, and the red one shows how much deforestation has occurred, which means there is no more forest in that area.
Great. Thank you very much. So then I have another questions to you, that you can see in 1994 the pattern of deforestation, in 1995 the pattern of deforestation, in 2008 the pattern of deforestation is something similar like 94, in 2009 also similar, in 2010 you can see similar patches of deforestation. But what happened in 2007? So much deforestation there.
I think it might have been a wildfire, or it could be cut down to make space for palm plantations, because these are the two options that usually happen in the Amazon area.
That is really great answer. That you also included like a location, and then you are very much aware of locations. Here, you forgot that the why in 2007 map it's we can see very high deforestation. What happened there? If we look at this temporal stamp like 1993, 94, 95, that's a 96, that's yearly basis, and 96 to 2007 there is a large gap, no? Large gap. So the deforestation is that deforestation is accumulation of 11 years. That's why that deforestation we can see very large area is covered by deforestation. And then the pattern is the yearly pattern is something it's again continue as before. But this the real answer here, you also need to see that those information is really important, but also we need to see that if we are talking about temporal, then the time stamp is very important, and that deforestation is maybe the things you explain may be true or may not be true because we don't have evidence. But evidence here from the map that we can see, that's accumulation of 11 years of deforestation, so that we can see large area. So this is very important. Many participants usually use this image in every lectures, and then most times they don't pay attention in this time dimension. That's great. Thank you very much. Thank you so much. So let's move to another slide. So there are many applications of spectral bands you can see in this table. So this table provides some example of spectral bands and their corresponding applications. For instance, the blue band is preferred for the analysis of water characteristics. If you are doing research on water resource management or something, then maybe blue band is very important. If you are doing forest biomass estimation or crop monitoring, maybe vegetation monitoring, maybe near infrared, maybe better, something like that. So you can look at this table in detail when you have time later. And here the spectrum of a microwave region. Here I want to highlight that let's understand this. The spectrum in this region is quite large. You can see here microwave, and then it's expanded here. This is there are several wavelength ranges from 0.1 centimeter to 100 centimeter, and also you can see that's represented by in the 300 gigahertz to 0.33 gigahertz in frequency with unique band code like P band, L band, S band, something like that. And microwaves with longer wavelengths than Ka bands, like in 7.5 nanometer millimeter, are generally used as radar. No? Beyond K band, we use here. And then this currently, maybe you need to remember currently what are the availability. So X band, C band, and L band are in operation in Earth observation satellite. For example, TerraSAR X is X band satellite, Sentinel-1 is C band satellite, and LS2 is L band satellite. Those data are available to use currently. So I think you need to understand there's C band, L band, and X band here. So more detail on this band. It's similar to the application of the spectral band. If you remember earlier slide, that there was a table that the table highlights which spectral band will have a which major application. That's similar to this table. Which band, which X band, C band, S band, or L band, P band have a kind of what kind of applications are there. If you are really working on like vegetation mapping, then which band of data you need to select, something like that. So this table can clarify that. So here also I'm adding this the screenshot of the SAR handbook here, which also help you to understand more if you wanted to see or if you wanted to expand your career in radar remote sensing. So maybe you may want to study this book. And this book is I'm also a co-editor in this book, and it's a we published this book last year. To if you want to explore, you can download this book. It's free of cost. You can just find in the just type SAR handbook, then you can get the link, download link there in the Google. And then it is also written in very simple language to explain very complex things. So if you want, you can do that when you have time. So there are some advantages of microwave signal. Try to read this image. So this figure provides a conceptual overview of the influence of sensor wavelength on signal penetration into a variety of surface types. The radar signals penetrates deeper as sensor wavelengths increases. So this is related to the dependence of the dielectric constant on the incident wavelength. So allowing for higher penetration at L band, you can see here, and you can also see the penetration level of X band, penetration level of C band, and L band. In vegetation, you can also observe like in the soil, like dry alluvial here, and then also you can see glacier ice here. So this this figure gives you a kind of idea that the which band will be better fits to your needs. So here you can see the effect of this the band. Notice the difference and the capability of different bands here. And this is X band radar image of forested area. What can you expect in the area denoted by this yellow circle? You can see here. Just we can see maybe this is a tree canopy. If you remember here, in the X band you can see only tree canopy here in the X band. And if you have a L band, then you can also see the trunk of tree. And here you can just you can see that maybe it seems kind of there something, but we are not so clear. If you wanted to be clear, let's see next image. Just have a look. Here you can see structure there, even below the tree. It's very interesting, very curious. And this is, you can see here. Here you can just see, you can imagine there are some lines, but we are not clear. But here, this is airport. This is airport. And this is a kind of military activity here. Maybe they have some kind of structure below the tree canopy. Here you can see. Here you can see. So there are different applications. So this is a P band image taken by aeroplane, and then the vegetation cover is transparent in P band, and because it has a longer wavelength, maybe 1 meter wavelength. Okay, let's understand a bit geometry, not in very much detail because we don't need that much level right now, but a little bit how this works would be we need to understand. And the figure is a schematic diagram of a radar observation geometry, where a platform is moving along a straight path at altitude H. You can see, and then this is a platform. You can think it's a satellite. And then, unlike most optical imaging system, which pointing their sensor towards nadir. Nadir is a vertical, vertical. But the antenna of the imaging radar is pointing away from nadir by a look angle. There is an angle. This is an angle. This is a look angle. And therefore imaging radar systems are side looking. This is a side looking geometry. So the radar image that you will be expecting in next few slides, that they are taken not from the nadir, not from the vertical space, but that is from the side looking, based on the geometry. So here you also need to understand synthetic aperture radar, because in radar remote sensing you will be hearing this word many times, and you will be using that kind of data, SAR data, SAR data, SAR data. As you remember, maybe earlier I said the SAR handbook. That's a very popular word. So you need to understand what is it exactly, what is SAR, how it functions. This diagram shows this in the figure. You can see this is a platform moving here, and different platform, and in different time period. Maybe the platform here it is moving in some time, coming from here to here, like that. No, so this is. So this shows the radar a satellite moving along the path. You can say it's a path, and the ground is like this, but in the space it's like this. And then this is a continuous strips of ground surface are illuminated parallel from the here. It's illuminating. Any object can be illuminated. No? And one side of the flight direction producing a long aperture by motion. So the satellite, because it's side looking, it can see the object when it starts from here. For example, the satellite is moving from here to here, this direction. Then it is looking here because of the angle, and then in different time period also it can observe that same point, same locations. No? So that is. So if we if we merge all this data, then that can create a long antenna. You can see long antenna. Maybe this is a 10 kilometer or 100-kilometer antenna you can see. So physically 100-kilometer antenna, it's really difficult to make it, no, in the space. So if we do some kind of mathematics and make a synthetic antenna here, so that called synthetic aperture radar here. As a result, a long antenna is created synthetically. This is a synthetic antenna, you can see, combining the information of many return echoes, because this object will send the echoes here. It's recording by the sensor, received as shown in the figure, such as long antenna is called, this antenna we call synthetic aperture radar. So that is not really appearing in the space, but that is, it is combining the data, combining these echoes that collected by radar sensor, and that creates that can capture this long the long data set, exactly physical, and that can be collected by physical antenna. So we call here, this is a synthetic aperture radar. SAR system is commonly used in satellite remote sensing. The SAR transmit microwave radar pulses toward a target from here to here, and then records. It will records the echo from here of the any target. That is we called radar backscatter here. So we need to remember backscatter. So synthetic aperture radar and the backscatter and side looking angle. So all these are very important, you need to remember. So that is very important. How imaging radar works. So this is I'm saying that it's a side looking, and then the backscatter, maybe this intensity is a backscatter. That's in gray scale. So the brighter, maybe that has a kind of radiometric pixel may have a higher value, and then the darker, maybe lower value, something like that. And then this is so since radar is moving, and then so if you look at this figure, it's a side looking. If you remember, if it is very physical, if this is a face-to-face training, so I could have make one antenna and then make the kind of a platform that moving. But here you can just imagine. There is one question: identify the direction for azimuth and range. And if you see here azimuth and range, this is azimuth. Azimuth is satellite direction. It's a flight path here, and this is a range from here to here. Is a range here, and then this is because of angle. It can capture the, for example, this and this. It will be the geometry will be fixed in the satellite. So this one is a range, ground range, and then this azimuth. I'm going back. Okay. So because of side looking, maybe the mountain topography is looking, it's tilting toward the satellite. So here I can see this is a azimuth, this is a satellite is running from here, and this is a range. So the satellite is moving from left to right and looking top to down, no? Top to down based on this image. Because of the side-looking geometry used in the mountain region, the topographic effects is clearly visible. These are the topographic effects in radar. So maybe you are now wanted to know how this SAR image is formed, how the data is received when it is received in ground station. So SAR image is constructed from the many pulses reflected by each single target and received by the antenna and registered at all positions along the flight path. Then image processing algorithm performs range and azimuth compression. You can see, if you see this raw data, then you cannot imagine whether there is a city or whether there is a mountain, whether there is an agriculture field. It's really difficult because they are all in electronic form. It's like a echo that received from the target, no? This one. And then there will be kind of the algorithm, software algorithm to process, and the range compression, you can see this level of image, and then azimuth compression, you can see the kind of the image that you can understand, you can interpret. So, and then this is a geocoded image here, and complete to which you can use for analysis. So this is there is a very complex engineering inside here, but you don't need to go in that detail. If you really wanted to do PhD, maybe you wanted, you can go. But here, maybe understanding only this process will help you how it is formed, because after all, you may going to use this image. So in radar, you need to understand the polarization. So in microwave energy, the polarization of the radiation is very important. Polarization refers to the orientation of the electrical field. Most radar are designed to transmit microwave radiation either horizontally or vertically polarized. So it's also represented, if it is horizontally then H, and if this is vertical then V. Similarly, the antenna receives either horizontally or vertically polarized backscattering energy, and some radars can receive both. So maximum 4 combination, there is only HH, HV, VH and VV. 4 combination you can expect that the both transmit and receive polarization, so which you can see in this also in this image. So if someone says it is single pole data, then you may expect only one of the pole polarization data. If someone says dual pole, then maybe you will be expecting two polarization data, any of them. And if someone says quad pole or full pole, then all full polarization data you can get, or you are expecting to get. So here the radar antenna from the satellite, that is also transmitting the pulses in horizontal direction and receiving the echoes in horizontal. Here transmitting in horizontal but receiving the echoes in vertical. And here transmitting from satellite the pulses to the ground or object in vertical but receiving in horizontal. And then here you can see transmitting in vertical, receiving in vertical. So these are, so like in Landsat or Astra image that I said that the Astra will have like 14 bands, and the Landsat will have like 11 bands, and Modi's will have like how many bands? 36 bands that we have explained in earlier slide. But in radar you will be expecting maximum 4. So if you look at these figures, so each bands or each polarization will have a different applications, so that we need to select the appropriate polarization for your application. If you look at this figure, it's taken in the same time, and you can imagine that what is the application. So look at these two pulsar images. Pulsar is a radar image from LOS. So HH polarization in left and HB polarization in right. HH is sensitive to flooded forest. So this is a sensitive to forest, flooded forest, flooding, no? Flooding. And then it is good for flood mapping. Then HB. This is HB image. If you look at only this, then you will be selecting. If you are working on flooding, then you will be selecting HH polarizations. If you look at this one, it's also pulsar image, and then just look at this, the rows here, and then HH polarization image taken in different time period in upper row, and the HB polarization taken in same time as HH in the row below. You can see same time, 20th June, 28th June, the same time. And then this is another year, 2008, 15 August. This is also another year. But this is HB image. This is HH image. You can easily detect forest degradation or clearance in the figure below, as indicated by red color. So you can see red color here. Here is you can see also red color, but not that much of dark. It's you see dark red color here. So it's easily you can even visually you can identify. So HB is sensitive to forest, non-forest, or forest contrast or vegetation structure and biomass. So this is very easy to see. So depending on the transmitting and receiving polarization, the radiation interacts with objects and get backscattered differently. So both wavelength and polarization affect how a radar images the land surface. So this is you need to understand. It's very simple. In radar, you also need to understand the scattering mechanism. As we see that there will be the radar system in the satellite that is sending the pulses, electrical pulses into ground, and it interacts with the ground surface, and then the whatever surface it looks like, and then it sends the echoes back to the sensor. That echoes will be recorded, and later we form the image and analyze. So that's why maybe scattering mechanism is also important to know. The tone in the images is affected by microwave energy interactions with object, which can be classified into three types of scattering: surface scattering, volume scattering, you can see in the here in the image, and then the double bounce scattering. So smooth surface such as water or bare land will have low back scattering, which will be in the image, which you will see kind of dark color. If in the image you see dark color, then that area may have like a bare land or water, and while rough surface such as forest, buildings, and will have a high back scattering, and it can be represented in kind of bright color in the image. You can see the image here. And then in radar we need to also understand what kind of distortions will be there. So the imaging SAR system is side looking. So that's why I was highlighting you the side looking. So side looking radar sensor with an illumination, it's perpendicular to the flight line direction. SAR image presents inherent geometrical as well as radiometric distortions. You can see here, and you can also imagine through this one. So you can notice that one side of the mountain, as you see in the figure, seems shorter here, and then the others. You can see the other side is longer, and the other side, the one side is like very short, which is geometric distortions. And at the same time, you may notice that one side of the mountain seems much brighter than the other, which is radiometric distortions. And this slide speaks very clearly, and there is also notes, so it is easy to understand. And let's see the geometric distortion. That's because of geometric distortion. What can be expected in geometric distortions? These figures also clearly shows you the geometric distortions. So main geometric distortion on SAR images are with their dependence on acquisition geometry. Acquisition geometry is already fixed in satellite. So three types of distortions are more prominent: foreshortening, layover, shadow, as indicated in the figure. When the radar beams reaches the base of a tall feature, a tall building, tilted away from the radar, foreshortening, that is we call foreshortening, occurs before it reaches to the top, like this one. And then the foreshortened slopes appears as bright features on the image. If you see the bright features. Layover occurs when the radar beams reaches the top of a tall feature. You can imagine very tall building in Islamabad, tall feature, before it reaches to the base, because radar signals it touches the top before it reaches to the base. So this effect on radar images looks similar to that due to the foreshortening. Small incidence angles also produce large influence from these distortions. So shadow occurs when the radar beams is not able to illuminate, because there is a mountain, and behind the mountain maybe radar cannot see any objects that is not illuminated. So the ground surface behind the tall features are slope. So large incidence angles produces large shadow area. So look at this one. This is the shadow because the satellite is moving from here to this way, and this is a range direction because of the looking angle, side looking angle. There is a range direction, this one, and this is a shadow. So radar cannot see. This is a foreshortening. This is layover. So this is if you look at this image, and you can see the differences as compared to the previous image. So part of the geometric distortion you can remove by performing terrain correction using digital elevation data. This figure shows the geometrically terrain corrected image where you can see the major differences in mountain areas representing real topography. Before it was showing that the short distance, than the other part of the mountain, but now you can see very clearly. And this image is a after radiometric terrain correction, so you are able to perform these radiometric terrain corrections, which remove the unnecessary distortions because of radiometric issues. You can see here, this one, radiometric issues, but here it is gone. After radiometric terrain correction, those brighter values are gone. Some of the radiometric distortions appears in the image of urban areas can be removed using the speckle filtering algorithms in software. Here you can see the SAR images representing urban structures in the left here, and the filter version of the images in the right, which is very clear and smooth visually, so that it's easy to use, easy to interpret. In SAR images, it's a radiometric distortion. We called the speckle noise. Technically, it looks like noise, but it is not. It is interference patterns. A cell is one cell contains many reflecting objects. The variation of many reflecting objects generates a speckle noise. This kind of noise, which looks not clear, not very clear. So filters, there are many radar filters that can be applied to surpass this noise, as you can see in these images here. Many noises are removed, and much of the features in the surface looks very clear. Okay, so these are the basics that maybe you need to know when you are talking about remote sensing. And remote sensing is the source for the data in GIS. So maybe in future you may going to use remote sensing data. Maybe this kind of basic knowledge will help you, and I hope you become a bit aware on this, so that if you are selecting the remote sensing as your next academic career study, maybe this is very helpful, and this may motivate you, and it will also make clear that okay, I want to choose only optical, I want to choose radar, or I wanted to choose both, because optical remote sensing gives us the information what we can exactly see in the ground by our bare eye, but radar also gives what we see in the ground, but more than that, because if there is a cloud, then optical sensor cannot give you any information, but radar can penetrate that cloud and still give the information what is happening in the ground. So there are many pro and cons in both, but understanding these two and then the trying to use both maybe will help you in your achieving the goals in your study or research or work. So with this, I have completed the concept of remote sensing with simple representation covering a range of essential things to know from optical and radar. Now there are many applications of remote sensing. You may see in this list here, covering from water resources to oil spill. From here, I would like to briefly showcase, since we don't have enough time, I'd like to go briefly some of the applications which may be useful to you, or which may be useful for navigating ideas and brainstorming for yourself. You can see that okay, this can be done. So maybe I wanted to do this. So maybe this is it's useful. So if you see this list, and then you can see okay, I'm going to do. I'm interested in disaster monitoring. I'm interested in forest monitoring. And my job is measuring motion of the earth's surface, understand the earthquakes or volcanoes. No? So how we can address those things? I want to showcase some example. Maybe we may not have time to interpret all those, but it will help you to understand. And then there are many literature already published in specific applications, so that you can focus on that. Okay, see this one. This is a land development monitoring, sector G13, Islamabad. Is there anyone from that area in this Islamabad sector G13? Any one of you are from there?
No, near
No. Any one of you
to
are
that.
here
I'm
from
Sidram.
Pakistan? From Islamabad?
Yes, sir. I'm from
Yes,
Islamabad
yes.
and I know this sector and the
Okay.
development of it.
Okay. So maybe you are familiar with this sector, but
Yes,
anyway,
sir.
I try
Yes, sir.
to
I know
bring
this.
this. Okay. So you can see this one is in 2007, September 7. This image was acquired in 2007, September 7. So then recently, maybe before pandemic, you might have visited that area. Maybe in recent years, maybe you have seen a lot of changes there. But how it looks like, and then the remote sensing have a power to monitor those. So let's see another figure here. You see, in 8 months, what happened in 8 months? 8 months is a very short duration, but you see here, lot of roads there. It's a uh, how can you say? It's a planning, no? Housing planning.
Yes, sir. It's developed now.
Yeah, it's here, no? In 2008, just 8 months. 2008, May 5. This image is May 5. Exactly same location. You can see the changes. And if there is no remote sensing, it's not possible. You wanted to know now what happened in the past, what was it looks like. If there is no remote sensing, it is not possible to do this. So this is a great application. In 8 months, in 8 months of time, what can be happen in Islamabad? Let's see this one. In 6 years, 6 year in time. No, it is in 2014 September, almost same season of in the first image. See how many houses you can count here. Even you can count from the satellite image. Okay, and then you can say, okay, this is a level, and there are this much of houses are developed during this time, 6 years. This is how urban is growing in Islamabad. You can trace, or you can interpret all those. No? And then in 2020 April 22, so just few months back, you can see what happens there. more houses were added in 6 years, and there are also some apartments, no? High-rise apartments are there, and there are also green space are also maintained. Some park are maintained, and then there are some park are also being developed. This looks like very nice, and maybe you might have realized, maybe you may be driving or you may be passing through this road. Maybe you can see that this is very nice housing colony. How it looks like from space, and how you can quantify. This is you can quantify. You can just digitize. Maybe you will be learning how to digitize today or tomorrow, and then you can digitize. Okay, location of each house, and you can digitize the road, road, and then you can digitize all park, and you can also digitize the shape of those park or space, how this is developed. So remote sensing is the only tool that can help you to understand the historical time series information. This is a temporal resolution. You can say this is a temporal resolution. If you say spectral resolution, there are 3 colors you could see, visible band, green, red, and blue. Combination of that, you can see this color. So temporal resolutions, and then also the spatial resolution is very high, high resolution, so that you can count all those. So this is very useful. You can do it for whole Pakistan. Also, you can do it only for Islamabad or any city as you like, and you can do it for your area of residence. It's very useful. Just you can go Google Earth and you can see that. Maybe some of you are already doing. This is very important. And I want to show you here a kind of 3D visualization for Kathmandu Valley. This is Kathmandu Valley, and you can see the mountain. And then if you can use, this is the image, satellite image taken in 1999 using the Landsat satellite, and we use 20-meter dam. And so that dam will provide you the topographic structure, and then how it looks like. Where are the forest area? Where the residential area? Where are these kind of rivers? So that you can easily visualize, so that the planners can understand what is all about, what is there. So this is another application. And then the land cover mapping, if you wanted to do, there is a step I have developed in 2009. It's also published in Remote Sensing Journal here. Step 1, you have to do this one, and then the step 2, step 3, step 4. You can see very detailed. You are really interested in this, in that papers. And using that method, I will show you this land cover mapping, managed land cover map in 1967, 1978, 1991, 2000, 2010. So using remote sensing, it is possible. Even you can think now, no? You want to create a map in 1967, and then you want to see how landscape is changing, and then maybe your objective is, okay, I wanted to do urban growth monitoring, how urban is monitoring, how agricultural land is changing to the other land use. Then this kind of map is necessary. To produce this kind of map, you have algorithm here, and then you have a kind of data set here, you can see. So this is another application. And then also using those knowledge, you can also predict the future using GIS. No? This is a bit advanced, but you can do that. So looking, the perspective is also important. So this is coming from my PhD and postdoctoral report here. And then, okay, this is a global forest tracking. I'm introducing here. I was leading global forest carbon tracking group in Japan Aerospace Exploration Agency before joining ECMOD. So during that times, I was working and developing all this kind of data set there. So here, 2007, 2008, 2009, 2010, if you are interested in monitoring globally, or if you are interested in monitoring only full Pakistan, whole Pakistan, then maybe this kind of data also very, very important. This is a 25-meter spatial resolution mosaic data, and this is not only 2010, but now you can receive like 14, 15, 16, 17, 18 yearly. It's free. Data is free. You can also exactly similar data you can get like 2007, 8, 9, 10, and then also corresponding year like 14, 15, 16, 17, 18. The map. If you are only interested in forest and non-forest, you don't have time to analyze. You can just download this data and then see how forest is changing. And then if you wanted to know methods, you can see these papers here. This is forest carbon tracking. How much carbon stock is there? And this is a radar image. This is a land cover map using that image. And this is a forest carbon density map using this equation. This equation is developed in this paper, this Thapa et al. Here. And then using that equations, you can see you can show where is the forest carbon stocks is there. I'm not sure in Pakistan you have a lot of forest, but if that is, then maybe biomass mapping is very important, and also quantifying that into carbon stock so that you can get carbon credit. And then this is like water resource monitoring. It's a cyclone Amphan. I think some of you are already it's familiar with this Amphan. It's a couple of weeks ago, and there was this event was happened, and this is you can see the color image can show you using the radar image that where the impact is happened. Here, red areas are inundated by storm water. Blue areas indicated pre-existing water bodies before the cyclone, and yellowish green areas are other land areas. So even just combining two images, two time period image, you can see this kind of difference so that you can do rapid assessment during disaster. This is also another flooding image. Two images are kept in the same location so that you can see you can visualize the flooding event there. Seen from Bangladesh in 2019. And this is glacier monitoring. Also, you can see Siok Basin, Pakistan, and there is also Siok Basin, Pakistan is in the B, and we have digitized. Our colleague digitized that area, how glacier is changing in different time period. The time period is here. Different line is representing in a different time period. This is glacial lake monitoring in Bhutan. You can see just you use the image, and then you can digitize. Maybe you are learning digitizing tomorrow, and then you can quantify different line, and then you can make a graph so that your managers can understand what is happening there, what will be happening there in the future. This is drought monitoring. If you are interested in agriculture, then the surveyor also developed the drought monitoring systems, and we will be covering that topic on Friday. Kiran Sakya will be talking about this. There is a drought applications. You can just use that applications to monitor drought in Pakistan. This is an example from Nepal. And the wheat area mapping in Afghanistan. Also, there is applications in surveyor. And this is you can quantify which area has wheat, which area doesn't, and how many province or will have what kind of area of wheat it's covering here. So this is another application. So with this, I wanted to download this book and read if you have a greater interest in the remote sensing applications. And this book deals with SAR applications. I am one of the editor in this book. This book is published by NASA. It's a global effort, and we are doing the interpreting all the knowledge in very simple language, also providing hands-on practices, hands-on data there, exercise, step-by-step exercise, where you can enjoy practicing and gaining knowledge there. Okay, thank you so much for listening me. It's gone for 1.5 hours, so we need more greater details. So now I wanted to stop here, and if you have some questions, I want to take those questions. Hello, do you
Excuse
have
me,
any
sir.
question?
Sir,
Yes.
Sir, it looks like your mic is far away from you, so it was quite hard to understand because voice was not clear. Can you please uh, look at your mic if we can understand better
So I think my mic is
for the next session?
for the next session. My mic my mic is in the same place as I am using even from yesterday, because I am using this you know I can say, I
sir,
think
I have
so.
a question.
And so yeah, I'm using this one. Maybe that's not be, it's not be a problem, but I don't know. Okay, so maybe in your side there may be kind of internet issues, but this video is recorded, so I think in the video you can also hear this very clearly, because I am using
Sir,
this
I
one
have a
as a,
question.
yeah, please.
Sir, I wanted to ask that as you have mentioned the applications of remote sensing, like we can do the tracking of land use, land cover change, the forest monitoring, and everything else. I wanted to ask that these are the things that we can also do through GIS. So, can you please elaborate? I'm a bit confused in it. That what's the difference in it, and how to use these things in all
Yeah,
these
so
applications?
yeah, that's a really good questions.
Thank
I
you.
think it's also very useful for all other participants. Thank you, Yunus. It's a really good questions. And so please think about remote sensing provides the data source. Remote sensing is the data source for GIS. GIS
Okay.
cannot make data. No? GIS is a system.
Yeah.
So
Yeah.
the
GIS
data
system.
comes from the, yeah, data comes from the from source. No? So one source is you go to field and then map everything. If you are civil engineer, then you know how to map it. And then
Okay.
the or survey engineer, you know how to map it. So you get the data from there. So one is you going to the field and collecting the data, and then you can bring it to GIS. GIS is a system, so that you can use it, you can analyze it, you can model it, you can do some mathematics, and so that is GIS is a creating map. The remote sensing is a replacing that survey, that is providing the data, and then that data you need to interpret, and to interpret you need GIS. So GIS comes after remote sensing, and don't take it separately. So remote sensing is a satellite system. So maybe you can see like a satellite remote sensing. So satellite is roaming there, and it will provide these snapshots of a particular area, and that area
Okay.
you interpret. So
Yes. Now I understand. Thank you.
yeah,
Thank
if you remember that the land, the methodology land cover mapping, then
you.
the
Yes.
also you remember, I also highlighted that that housing in Islamabad, no? So
Yes.
if there is no remote sensing, GIS cannot do anything.
Okay. Okay. Thank you so much, sir. Now it's clear.
Thank you. Welcome. Okay, very good. Actually, that's a good question. Maybe other participants also getting confused.
Yes.
Yeah, any other?
Hello. Hi.
Hello, who
Can
is
you
this speaking? Yeah,
can you hear
I have
me?
a,
Kuratulana. I'm Kuratulana. So can you
okay.
tell us? I have one question. Can you tell us the links or site where we can download these images? Like I have to work on the change detection in the vegetation cover in Pakistan. Like um, if I want to do work on the decadal change, like with the gap of 10 years,
Okay.
the vegetation cover in Pakistan, then
Okay.
from where I can download this data.
Okay, so that's also really good question. And then the where I can get these remote sensing data. So you need to understand two things. One is whether these data are free or commercial. So if it is commercial, then you need to buy. If the data is free, then it's easy to find it. So for instance, if you are working for company and then the company, for example, the company doing a dam project, and dam project will have a kind of a big amount of money, and they also need very precise information, very detailed information. Maybe they go for commercial. And then if you are doing research and only you are interested in vegetation monitoring, then maybe you don't need to go for commercial. Maybe you can go for free and open source data. And for this, like Landsat data, Landsat satellite has like 40 years of archive. So you can go back to many years, many decades, no? 40 years of archive Landsat has. It started in 1972 and it is still running until today. It will go more on the future. They have planned until 2030. So you have a long duration. So Landsat data has 30-meter spatial resolution. You can just type Landsat data in Google and you can find the link. Downloading Landsat data, then you can find the link, and you will be guided to USGS website, and there is a detailed instruction how to download, how to register, and how you can get it. So that is one. Another is a Sentinel-2, is a optical data, and Sentinel-1 is radar data. So Sentinel data, I think it started from 2014, and that is the data is provided by Copernicus. And if you just type in the Google, download Sentinel-1 data or download Sentinel-2 data, then it will bring you to Copernicus website. You can get from there, or also there is a data download system in Alaska satellite facility, ASF. You can also download from there. And for example, for vegetations, maybe you are interested in L-band data, then you can get it from JAXA website. You can also type just LOS satellite or L-band data download, and then it will guide you to JAXA website so that you can download. So before downloading, they will ask you to register your name and your email, and then they will send you the instruction guidelines how to download that. So that way you can download.
Okay, thank you very much. Thank you.
Sir, sir, may I add some databases?
Yes.
Sir, she can download the data from UCI repository. UCI repository is a top repository where you can find all kind of data, and other one is Kaggle, and third one is github.com. From these you can easily download the data, and easily even you can find the code of the data.
Thank you,
Can you
Mehak.
send
Mehak,
the name to the messages and the teams?
Sorry?
Can you send these names to the messages conversation in the teams so that we
Sure,
can?
yeah.
I'll send it on WhatsApp.
Thank you, madam. What is your good name? Which told about the
Shagufta
UCI?
Nas.
Shuguftanas. Okay,
Ma'am,
thank
it's Shagufta Nas. I'm currently working on the same project like land cover and land usage, and cultivated land, non-cultivated land, how much area water is covered in our forestation. So currently I'm using these databases
Okay, actually,
in the
ma'am,
field of computer science.
I'm doing on the drought simulations and predicting the trends and patterns in Pakistan. I'm doing PhD over it, and for the validation of my research, I have uh, to cover this topic about the change in detection or monitoring about the vegetation cover in Pakistan. That's why I was asking.
May I add to this?
I have one question to Sagupta.
Ji
Sagupta,
sir.
it shows,
Ji sir.
yeah, it shows that it's here I can see Mehak Sikandar. Mehak Sikandar and Sagupta is the same.
No,
Okay, so maybe the name is showing it. Okay, now it's Sagupta, yeah. And I think you also have kind of idea that there may be some kind of free data available portal in Pakistan. Maybe because you have like Institute of Space or some other. Do you have any idea? Sagapta, are you there?
Sorry, sir. Can you please repeat your question?
Yeah, I think you have more knowledge on data availability, and if you know if there are some kind of Pakistan, the agency in Pakistan, they also provide data that will be useful to
Sir,
all participants.
Sir, I know about the UCR repository where the where you have a word data. I don't know about the Pakistan, but I have currently worked on the overall data. So one is UCI and other one is Kaggle, and third one is on GitHub. On GitHub, you can simply post your problem that you want that kind of data, and the community will answer your question. Or simply simply they can provide you the link.
Okay, that's great. That's useful
Sir,
to
in
all participants.
Pakistan, sir, I want to add, in Pakistan, Ministry of Climate Change and the Meteorological Department, PMD, Pakistan Meteorological Department, provides all kind of data about environment and climate change, etc.
Okay, that's great. That's really good. I think useful to all participants. And I saw that hand it's raised by Mehak. Mehak, you want to say something?
Yes, yes. Basically, I have a question. If you go back to the page number 20, that is related to the spectral resolution, there are some bands, right? Page number 20.
Page number 20.
Can I share my screen? I have already opened that.
It is here. So 20, 20, 20. Okay, 20.
Yeah,
Yes, 20.
yeah, this
Yeah,
one. Like what these bands indicates and what does these colors represents, and isn't difficult to convert these data into the topographical features.
that's a good question. This is just a schematic figure that I prepare for teaching purpose. And let's see, for example, Landsat 8. No, Landsat 8. You see here. Can you see my mouse?
Yes.
Yeah. Okay. So Landsat 8. Landsat 8 I am showing because it's very popular, and then the Landsat has a series. There is a Landsat 7 and Landsat 1, 2, 3, 4. It comes to Landsat 8, and you need, if you wanted to go for historical there. And the color here is it doesn't represent anything, but I tried to show that the, for example, the Landsat band 1 and 2 are in this wavelength. This is a wavelength in nanometer wavelength, and this wavelength that we are talking previous slide, that this wavelength is a blue, and then there is a green. No, just
Yes.
trying to show. I will show you another here. No, here is a blue, green, red. No, and that is we call visible. For example, I also want to highlight, tell you that let's say you use your smartphone to take picture, everyday picture, no? And then you see that picture, and in that picture you see many colors, and all those colors are the combination of blue, green, and red. We can say red, green, blue, RGB. RGB. Combination of RGB, you can see millions of color there. Beyond that, our eyes cannot see. But the satellite sensors are designed to see beyond that also. So here this color is you can link to that, like this blue band here, and this is green band up to here, and this is red up to here, and this number, this is a wavelength, no? This wavelength, and if you remember here the numbers, you see 400 something like that, 300 to like 700. You can see only this level, this color. Beyond that we cannot see. Beyond that there is still color, but we cannot see. And this beyond 700 there is still color, but we cannot see. So in this figure, don't be confused about this color. Oh, yellow. Oh, no, don't be confused. So this is a kind of 7 is a Landsat, like this is Landsat 7. Landsat 8, Landsat 7, no? This one. In these two satellites, like band number 7 has this kind of wavelength from here to here. You can accurately find in the internet, but here in the figure you can see from here to here, and then but in the Landsat 7 you can see this band is wide, no, wide from here to here. So that is all. That's only the I wanted to show here the spectral, because topic is the spectral resolution to identify differences. And the for example, in MODIS, you see, even in blue there are many bands, 1, 2, 3, 4 bands, no? And then blue, and then green 3, and red this one, and there are 36 band in MODIS. In Aster 14 band, and different band will have different applications that I also explain very briefly somewhere. Yeah, for example, blue, what is the application? Okay, blue for water, green water quality study, sediment, chlorophyll concentration, red for vegetation type, assessing plant condition, delineating soil, geologic boundaries, something like that. You need to read that. So that's all. Okay.
Like we get the data from the satellite in the form of waves, but my question is how we can convert the data into the useful information that can be understandable.
So if you downloaded the data, and then how to convert?
Actually, she is
The
asking
data.
about the data processing, how we will be processing the data.
Yeah. So that is, I think, maybe in this training we are not covering how to process the satellite imagery. The satellite imagery processing is a different training, and here what we wanted to show you that the what you can, when you study GIS, then there was also earlier one question. Yeah, GIS can do everything. Why remote sensing is needed? Then I clarified that the data comes from remote sensing, so that GIS can create line, GIS can create polygon, GIS can create the point, so that we can analyze. So maybe today or tomorrow you will be going to see, and where you can be using remote sensing data to digitize those things. But analyzing remote sensing data directly, maybe we cannot cover in this very short term, in this course, because this course designed in a way that make the participants aware what is available there, and whether that it's interesting to them. If they have if you have interest, then I want you to read these papers that highlights the how to process. And if you really want, I also gave you this book since in many years, and that we found similar questions, and people need some guidelines how to process the data. So if you follow, if you read this book, this book, can you see this one, the SAR handbook?
Yes, I can see
Yes.
that.
Yes, this handbook it's a for SAR data processing, and it will tell you where the data are, how to process the data to make useful information, and how to use that information for decision making.
Thank you so much.
And this book is written in very simple language, so everyone can understand. And there is a step-by-step guide. You can process the data. Okay. And if you have any questions after reading this, you can come back later again. You can write me email so that I can explain you. Maybe not during this training, you may not have time to go this through, but in future.
Sure, thank you so much.
You're welcome. And also, since you have this kind of interest, please, we will ask you final day, that asking you to fill up the post-processing, post-training assessment. During that time, so please input this kind of things there, so that we can, if there are sufficient participants, maybe we can make plan for running kind of how to analyze satellite data, or kind of advanced training later for you guys. Okay.
Excuse me, sir.
Yes.
I just want to tell something for all the participants, that if they are interested to take the climate data, so one participant has mentioned that we can take it from the Pakistan Meteorological Department. There are two types of the data given: past data and the future data. Future data is always simulated data. So these are the projections, and these projections are available for different types of the models. And on the website even you can find the Preci data, that is for 4.5 and 8.5 RCP scenarios. These are available on the website. You don't need to go to the meteorological department, you can find that on the website. And the other thing, another open source climate data website I want to tell you, that is the Climate Explorer. You can go over there, and you can take the monthly observation, daily observation for different types of the data and meteorological data. And thirdly, if you want to take the socioeconomic data, for example population data, then you can visit this Pakistan Statistical Bureau of Pakistan, and its website is pbs.government.pk. You can take data from there. And one question is from my side, from where we can take the soil data available on the net. I know that Soil Survey of Pakistan provide the soil and land cover data, but if someone knows about the open data source, kindly tell me, because I need that. Thank you.
I'm not sure if the other participants knows where the soil data is. I think there is a soil moisture monitoring satellite there. I'm not sure exactly soil moisture data, where it is available, because I'm not doing this kind of
For
research.
soil moisture, SAR data, AMSRE data is available, but that is very coarse, 25 kilometer or like that. Soil for soil moisture,
Okay, that's
AMSRE.
okay. So maybe you can type that word in the chat box. So now I wanted to ask participants. I'm sharing this screen. Can you see my screen?
Yes, we can see.
Yes.
Yes. And this is I'm confirming that the name. Please see your name, and
Yes.
if spelling is correct.
Yes, it's
My
fine.
actually it's number 9, Jaweria
Number 9.
Shamshad. SHAM SHAD.
SHAM.
Yes. Yes.
Okay. Some.
SHAD.
Okay.
SHAD. Yes.
Now it is okay.
Yeah, it's fine.
Yeah. Okay. So anyone, because in printing in certificate, it's sometimes I wanted to confirm the spelling.
I can't see your screen.
You cannot see my screen. I think it is correct, because we collected that from your the form that you have filled out, and I think this website you have visited many times, and you also provided a WhatsApp ID. But today I wanted to just finalize this spelling name, so that I can send this name to print certificate. Looks like it's fine.
Yes, sir, it's fine.
Okay.
Yes, sir.
Okay. So there will be no complaint to me. Oh, my name spelling is incorrect.
No, it's fine. It's fine, sir.
Okay. Okay, I will send this today to certificate printing department. We have a printing department, different department. So thank you so much today. And then I think I wanted to close this session and looking forward